change direction for free. And this allowed people in history to take advantage of the fact that they had bodies which had mass, and the force of gravity can be used to do a lot of useful things simply with the use of a rope and a pulley. And that concluded our dynamics in one dimension section, and we moved on to dynamics in 2 dimensions. And in terms of our kinematics section, the first main branch, when we looked at kinematics in 2D, we looked at projectile motion as well as one other type of motion. Who remembers what that second type was? Kinematics in 2D. Circular motion. Circular motion. That's where we are headed. Projectile motion, we knew that, or in kinematics, you're simply told that the acceleration is in the x direction is 0, and in the y it was negative g. But with dynamics now, you can see why that's actually the case. In projectile motion, you only have force of gravity, which only acts in the y direction. And so if you want to look at the x component, the overall forces acting on this object in the x direction is 0, meaning acceleration is also 0, which is what we have used. And in the y direction, you'll do the same through a similar analysis. You got that the acceleration is negative g and independent of mass. However, projectile motion is not very interesting from a dynamics standpoint because you're only dealing with the force of gravity. The more interesting motion for dynamics is circular motion. And so that's where we're going to focus for this class. Circular motion. Now let's begin with the trip down memory lane. So recall, angular position, we call theta as a function of time. And this had units of radians. We also had angular velocity. Which was omega t, and that was radians per second. The speed, the actual speed in circular motion, v was equal to omega r. And this has units of meters per second. And of course, we have the different accelerations as well. The angular acceleration. It's alpha as a function of time, which is radians per second squared. Centripetal acceleration, which is v squared over r, or omega squared r. This was meters per second squared. For the tangential acceleration, at is equal to alpha r. This also has units of meters per second squared. In circular motion, we want to view it, let's say, on a plane. So it'll look something like this. So the circular motion occurs on a plane. Now here, x, y, z coordinate system is not ideal. So instead, we want to use what is called the RTZ coordinate system. Now, before I go over why RTZ coordinate system is better, let's first just get an understanding of what the RTZ coordinate system even is. So our object is going to be moving in that circular trajectory. And so let's say at a certain point, our object is right here. The origin of our coordinate system is going to be the location of our object. So, what this means is the object is going to be moving in a circle constantly throughout. If the origin is where the particle is, your origin is constantly going to change. Okay, so that's just one of the natural side effects. It is going to constantly change. So it changes with time. Then we have the R, T, and the Z directions. R is the radial direction, and this is towards the center of circle. So if the object is here and the center of the circle is there, this will be the R direction. That is going to be the R direction. T stands for tangential. Which is simply tangent to circle, and by convention, counterclockwise is positive. Counterclockwise is positive. And so then the tangential direction at this point will look something like this. This will be the tangential T. Then we have the Z coordinate system, Z direction. Essentially, we ignore this, but this is perpendicular to the plane. It's perpendicular to the plane of circular motion. Meaning, here, that is going to be Z. So we have that. Let's say if the particle was over here, this would be the R, this would be the T, and that would be the Z. That's right angle, that's the right angle. So the RTZ coordinate system is much, much better to use than the X, Y, and Z. Except, you guys don't believe me yet. Because you still have this question in mind, why RTZ instead of X, Y, and Z? So far, I just made this as an assertion that the X, Y, Z is not ideal. Now you guys need me to convince you of that. Is that true? It depends. All right, I'll just skip this. I'm just kidding. And the answer is going to be pretty clear when I give you some additional information. A particle in uniform circular motion has the following velocities as well as acceleration. So we can have a velocity in all the different directions, VR, VT, VZ. There's also acceleration in all different directions, AR, AT, and AZ. If we use the RTZ coordinate system, VR, in a circular motion, VR just means, is it going towards the circle or is it going out of the circle? If it's constantly moving in a circle, Are we getting closer to the center or further from the center? And the answer is no, so VR is going to be 0. If VR was positive, positive R is pointing towards the circle. If VR was positive, then it would spiral in like this. But in circular motion, it doesn't do that, so VR is equal to 0. The tangential velocity is simply its speed, and from our circular motion section, we know that it's simply omega r. In z direction, is the particle moving above or beyond the plane? So if Vz was positive, then our object would form this nice helix. But is it doing that, or is it just moving in a circle? No, it's staying on the plane, so Vz is going to be equal to 0. The acceleration in the r direction from our circular motion section, this was v squared over r, or omega squared r. So you just need some of those velocity components as well as the radius of your circular motion, and then you are good. In uniform circular motion, the tangential acceleration is defined as 0. That's what it means to be uniform, that you're not speeding up or slowing down. And the acceleration in the z direction, that is equal to 0. This is why you want to use the RTZ. Look at how many zeros you have. It makes your life much, much easier. If you use the XYZ, your RNT component, or your your x and y components are going to look something like this. Your x and y components of your velocity and acceleration are going to look like that. If you want to use these, or just those zeros, or just one of them is VR or v squared over r, something along those lines. This is why RTZ is much, much more convenient. Because of all those zeros, and a lot of the math becomes much, much easier. The only thing that it requires is you to change how you're observing your actual system. So whereas XYZ, or in XYZ, the expressions would be very complex. But this is why the RTZ is beneficial. Now recall, in circular motion, even if speed is constant, velocity still changes. You guys remember that? In circular motion, the direction of your velocity constantly changes. So your velocity is changing just because the direction is. This means system is accelerating, or has acceleration. Do you guys see where I'm going with this? This is how we're going to make a connection to dynamics in 2 dimension. All of this so far was kinematics. For dynamics, that's about forces. And we discussed Newton's law. If an object is accelerating, what does Newton's law tell us? That there is a force. Therefore, system has a net force. just to make it move in a circle, there is a force acting on the system. And now the question is, well, what is that force? So question, what is F net for uniform circular motion? Answer, all we need to do is apply Newton's second law. Sorry. So the system has acceleration, and we discussed in the circular motion section that this is in the radial direction, AR, we discussed that it was centripetal acceleration, which I also noted was the acceleration in the radial direction. This was v squared over r, or omega squared r. All right, is this ringing a bell? So in uniform circular motion, the force is in the radial direction. So you want to do the force balance in the r direction. This is going to be mass times the acceleration in the r direction, which is equal to mass times v squared over r, or mass times omega squared r. This is Newton's second law for circular, we'll do this, uniform circular motion. What we did was we began with Newton's second law and just replaced the acceleration value with something that we always know to be true in circular motion. So Newton's second law for circular motion is this: net force in the r direction is equal to one of these, depending on which velocity parameter you have. So without this force, object travels in a line, not a circle. Now, just for completion, just so you guys are clear, the net force in the r direction is MAR, which is mv squared over r, or m omega squared r. The net force in the tangential, which is equal to mass times acceleration tangential. Well, we discussed in uniform, the acceleration in tangential, this is equal to 0. So the net force in the tangential direction is equal to 0. Likewise, the net force in the z direction is MAZ, which in the z direction, the acceleration is also 0. So this is the full, or actually, well, yeah, this one is good enough, but just so that you guys are convinced, in the t and the z, the net forces are equal to 0. Now, how this becomes relevant is in quite a few different scenarios. Now, one of the things that I can do is, lasso Sam over there and put him on wheels and then spin him around. That's one of the ways, but another way is in circular orbits. So analyzing these astronomical bodies and such. So what we're going to do is, let's do a thought experiment. Let's say this is the Earth. This is the Earth. And we are going to have a, let's say, a high tower, H. So consider a tower with height H. And it shoots a rock horizontally. So what we're going to do is just shoot a rock with continuously increasing speed, and then let's observe what's going to happen. So we're going to start shooting at very low speeds. At low speed V naught, the trajectory of the rock is going to look something like this. Right, parabolic. Right, this is just a continuation of projectile motion. Here, particle travels a vertical distance of h, meaning from here to here, it traveled roughly h. I'll say distance roughly h. But let's say we decide to shoot it slightly faster. Then the rock is going to look like that. At higher V naught, the vertical distance is now much, much greater than h, right? It started up here, but it must travel this entire distance. Do you guys see that? Well, why stop there? Let's shoot it even harder. When you shoot it even harder, it's going to shoot out, and then it's going to continuously try to reach the Earth, but the Earth is curved. So it's constantly trying to reach the Earth, but it never ever manages to do so until it hits you in the back of the head.
How?
Because gravity is pulling in on it.
Wouldn't that just make it land on the, at least on like the opposite side of the tower and not all the way back at where it's launched at?
Opposite side of the tower? Yeah, it's sitting right here.
No, I meant like on the opposite side of the globe, like on the bottom.
So like you
Just
would
landing
expect it to do something like this?
Yeah, or maybe a little closer than that, but.
But at a faster speed, so this will happen. As you keep increasing speed, it'll hit here, then it'll hit here, and so on and so forth.
So that's just a really, really fast speed.
Yeah, but at a fast enough speed, you're going to get to a point where the rock is constantly trying to touch the ground, right? It's curving down, right? It's curving. But the Earth is also curved. So as the rock is trying to curve and hit the Earth, well, the Earth is also curving, and it will never actually, the rock will never ever hit because the curvature is the same. What shape did we just make? It's a circle called circular motion. So at higher V naught, the particle is always in free fall. But never hits the ground. this is considered an orbit, which is a closed, where did I define it? Oh, it is a closed circular trajectory. What does closed mean? In the first two scenarios, there is a definitive beginning point and an end point. Beginning point and an end point. Okay, just assume the tire isn't there. In this one, because the orbit, the trajectory, actually directly overrides the previous one, well, where did it begin? Or where is it ending? There is no defined point, and that is what is called an orbit. And at this speed, the v0 is defined to be what is called the orbital speed. That is the speed to maintain orbit. Well, we can even shoot faster than this, theoretically, right? As long as you have enough gunpowder. Now, if that happens, it's going to spiral out of control. So at higher v0, rock escapes orbit. Now, all of this was assuming negligible drag. And this is the basic principle in which the satellites of the world actually operate. But in the real world, is drag, can you just ignore drag? No, you can't. So all the satellites have little thrusters with enough fuel, and then so every now and periodically they shoot the thrusters to make any corrections. That is actually arising from drag. So that's how they account for it. Well, now this leads us to a question. What is the orbital speed? Not just in terms of a qualitative definition, but what is the number? What is the number? Can we predict it? And to answer this, we ask an alternate question. What are the forces on the rock? So we just care about the orbital speed. So let's say the rock is here at some point in time. Also, the rock is there at some point in time. The rock is here, so on and so forth. What is the force on the rock at these points? Anyone? No?
Gravity.
Gravity! Which direction?
Towards the center of the Earth.
Towards the center of the Earth. But what direction is that in terms of our coordinate system? R! All of these are in the R direction. Now, if you use the X, Y, and Z coordinate system, guess how much trig you have to do? You have a lot. There's all these angle dependencies. So just use the RTZ coordinate system. Just consider a single scenario. You've taken care of all of them because all of them are pointing in the R direction. And the answer is force of gravity. And this is in the R direction, so all we need to do is consider the net force in the R direction, which is the force of gravity. Newton's second law tells us that this is also equal to mv squared, which is equal to mg. But in circular motion, or orbit, Newton's second law tells us that this is mass times acceleration in the radial direction. And you can see that the different masses cancel out. But in orbit, you have achieved circular motion. Meaning the acceleration we can replace with v orbit squared over radius of the orbit. This is going to be equal to g. Meaning the orbital speed is going to be the square root of the radius of the orbit times g. This is how fast you must launch, at least just straight, to get something into orbit. So here, if this is the Earth, and this is the orbiting trajectory, this is radius of the orbit. Our orbit isn't just the distance from the surface, it's the distance from the center of the Earth. So, I'm sure, where are satellites orbiting? You guys would say, way up there, right? Well, technically, you can just as long as you have a fast enough, gun or launcher or whatever, you can get a satellite like 10 feet off of the surface. However, you don't see those because there is so much air here, there is so much drag that you're gonna have like infinite amount of rocket fuel to maintain this speed. And it's not just for collision purposes, it's actually very, very expensive to maintain this speed. And that's why all the satellites are way, way, way up near the edge of or past the atmosphere, so that there's very negligible drag, and it's only just a little bit of fuel here and there to make the corrections necessary. Yeah, question.
Does that mean that there's basically no drag at all up there, or is that there?
Yeah, it's very, very small. Like, you try to go up there and take a breath, you're not gonna get it. Yeah.
But that doesn't mean that there's zero drag.
Right, there's little, yes. And there are many, 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 many satellites up there nowadays. And it's so that if you're like, I don't know, I think it was like 50 miles within the next satellite, that's considered like a near miss collision or something. But that's like how, yeah. But at that speed, you're going pretty fast, because, right. Let's actually do this. The radius of the Earth is 6,000. Can somebody do this? Radius of the Earth is 6,400 kilometers, meaning it's 6,400,000 meters times 9.8 meters per second squared. Square rooted. Can someone tell me what this number is?
7,000.
Huh?
7,919.
This is meters per second, which I believe, 7 kilometers per second. That's like 3 miles per second. That's how fast the satellites are kind of orbiting if it was at the surface of the Earth. That's if the satellite was right here. Satellites are orbiting miles and miles and miles above the surface, meaning this number should be, I don't know, like put a 1 in front of it. Okay, maybe it's not that much, but let's just say it's 10 million. Then what does the number become? 10 million times 9.8 square rooted.
$3,130.
Huh?
3,100.
Wait, it can't have gone smaller. Wait. Did you do 1 million or 10 million?
Oh, I think I did one more. Yeah, 9,899.
Yeah, 9 kilometers per second or like 5 miles per second. Right? That's really fast. So if you're 50 miles away from each other, that's only like a 10-second, right? 10-second miss. Yeah. So that's how fast the satellites are traveling. So pretty fast. So that's circular orbits. But let's do, and this is where we'll end. I know the class is going to be short, but the calc-based class asked a bunch of questions.
Yeah.
And we actually
Good enough.
ended their class 10 minutes early because I had covered this for them last class, like somewhere up to here. Or I actually covered, I think, all of this last class, but I didn't do it for you guys. And we were about to start a major section, and I was like, well, if they ask a few questions, we won't be able to get to where the previous section got. So we'll be ending class pretty early because you guys didn't ask anything. All right.
I love the calc class.
All right, let's look at the tension in a hammer throw. Huh? Now the hammer throw is a traditional track and field event. Hopefully everyone knows what I'm talking about. Now this is a physics question, so I know that the hammer throw, when they throw, the thrower is kind of off at an angle, and they are throwing with the rope and the trajectory. Right, it's kind of off at an angle, right? They like kind of rotate. All right, this is not the scenario that will be considered. Instead, we're just going to be during their, I guess, like initial momentum build-up phase. Or the easier scenario to consider is we're just swinging the rope around, right? That's the arm. So he's swinging the rope around like this. So this is a scenario we'll be considering. So Bob is spinning with a angular velocity omega with arm and rope length, we'll call it L. Right before launching a hammer with mass M. The question is, what is the tension right before release? What is the tension right before release? Well, this is a dynamics problem, and so we always want to begin by drawing a free body diagram. Our origin is going to be where the rock is, so the rock is going to be right here, and so we need to make sure that we're going to be drawing the correct axis. So this is the radial direction, this is the z direction, and the tangential is going in and out of the page. in and out of the page. So we're drawing the free body diagram for this specific instant in time. What are all the forces acting on the rock? Or, sorry, not the rock, the hammer.
Correctly.
Which direction?
Straight down.
Straight down is which direction?
Opposite Z.
Negative Z is correct, right? Force of gravity. What else? What else do we have?
Tension, R direction.
Tension in the positive at R direction here. Do we have any other forces?
Maybe drag.
Well, no, ignore drag. Ignore drag. It's too hard. Alright, this is it, right? But it's wrong! We only have two forces that is correct. Force of gravity and tension, those have been correctly identified. However, there's an issue here. Because the net force is down, there's nothing that's offsetting the force of gravity. This is an unrealistic problem because this will tell us that the rock is actually going to droop a little bit. So maybe I did trick you guys a little bit. It actually does droop by some angle theta. So the correct free body diagram, so this is wrong. The correct drawing would have been force of gravity. This is R. Tension will be off at some angle theta. Now the question was asking for tension. Tension is equal to what? So if you look at our free body diagram, tension is going off at an angle. But you can see that tension is the only force that's acting in the radial direction. So we want to do Newton's second law in the radial direction. But what are the forces in the radial direction? Well, what shape do you see here? Right, trigonometry is still not going away. So here, we have our tension triangle. This is theta. This is the radial direction, which is going to be T sine of theta. So our force balance tells us that the net force in the R direction is tension, the radial component of the tension, which is going to be T cosine of theta. This is cosine of theta. Why did I write sine? Right, this is adjacent. And Newton's second law will tell us that this also has to equal mass times the acceleration in the radial direction, which we know to be m omega squared r. But r, we are told the arm and the rope length put together, that is length L, meaning we can replace this with L. So when we put both of these together, we get T cosine of theta as equal m omega squared L, or T is equal to m omega squared L over cosine of theta. Well, do we know mass? Yes, we are told a hammer has a mass of m. We know that. Do we know omega? Yes, we are told that that bob is spinning with omega. We are also given L. Do we know theta? And we don't know theta. Well, luckily, we didn't fully exhaust our information because we only looked at the radial direction. We have the second direction in the z. What are all the forces acting in the z direction? Well, we see that there is a z component of tension, and it's acting up. So it's positive Tz. And we have force of gravity acting straight down, so it's minus force of gravity F. Newton's second law also tells us that this has to equal the mass times the acceleration in the z direction. But in this case, the acceleration in the z direction is equal to 0. Meaning this, Tz minus Fg has to equal 0. But what is Tz? You can see that Tz is T times sine of theta. Meaning T sine of theta is equal to mass times gravity. Or T is equal to mg over sine of theta. Well, look here. We have one expression for tension and another expression for tension. If A is equal to B and A is equal to C, what can you say about B and C? That they must be equal. So, putting both of these together now, we get m omega squared L over cosine of theta is equal to mg over sine of theta. Masses cancel. Multiply the sine over onto the other side and divide by omega squared L. And who remembers what sine over cosine is? And this is tangent, that is correct. So tan of theta is equal to g omega squared L, meaning theta is equal to the inverse tan of g over omega squared L. And so now we know that. And then we can plug our theta back into either one of these, and then we are finished. Except we're not. This is wrong. I'll give you guys a minute, and if anybody can spot what my error was, I'll give everybody in the class 2 extra credit points on the quiz because the calc-based class could not find it.
Oh, did it?
I'll give you guys 2 minutes.
Oh,
Because they had twice the class size, so they have like roughly 50 students, and they couldn't find it. Well, I'll give you guys a few moments.
Is it because one is tension in the R direction and the other is tension in the Z direction?
No, that is okay. We properly accounted for the directionality with the trig.
Oh.
So that was okay.
Are the arm and the rope connected?
Yes. It's definitely identifiable, but you guys are kind of running out of time. I'll tell you this, it's not a math mistake. Because I want you guys to get the points. Can't make it too easy. My algebra's fine, most of it's fine. There's one issue. I pulled a fast one on you guys and you didn't notice. Yeah.
This is a long shot, but is it because we're trying to find tension, not the TR/TZ? We need to find the hypotenuse instead of setting TR.
Yeah, so by doing this, we are actually getting the actual tension, not just the R component.
Oh, okay.
So when you do T is equal to TR over cosine of theta, we're getting rid of the R component and actually getting the tension, which is what we're looking for.
Okay.
That's not it entirely, but something with the hypotenuse.
It doesn't have to do with like that there's mass in the Z direction or acceleration.
That was accounted for here with the force of gravity. That was
Oh shoot.
here. Right, if it's not the math, where could I have gone wrong? Oh, yes, this was wrong. But this is correct.
Is something wrong with the force balance equation?
Yes, but you have to be precise where.
Is that just how acceleration is?
No. Yeah, yes.
Oh.
No, but you have to, what is it specifically? Do you know the answer? And you're out of time though. Alright, one final shot.
Well, acceleration in the other direction is not omega squared L.
No, what is it?
It's
Something else.
wait. Well,
Or why not?
What do you have to
Why not?
Well, because tension acts at an angle. That's why. And
So
omega would have to, you have to consider the cos. You would have to essentially. You'd have to do like omega cos theta or something like that. You'd have to consider the fact that it's at a different angle.
why?
Because
Or what? Like, what's the issue? Like, out of here, what is the issue?
that's assuming that tension.
No, I know that's a serious. Alright, but what must change? What is wrong here? Is anything wrong?
Yes.
What, yeah.
Come on,
What is it?
Come on.
Which one?
Get it, bro. Come on.
What is the issue?
Is it?
Wait, is it L?
Yeah.
Yeah, you guys all get points. It is L. The reason is, as soon as, right here, when it's at an angle, essentially, we do not have a, if you just look at the overall shape of the circle with the person standing right here, we make a cone. This is L. Acceleration in the radial direction is omega squared times the radius of your circular motion, not the hypotenuse of that cone. So, it is this That is the radius of our circular motion. Does that make sense? So if we actually just zoom in right here, what shape do we have? It's a triangle. It is at an angle theta. This was the arm and the rope. This is L. But for circular motion, you care about the trajectory of the circle itself. So, this R is of your circular motion, so we'll call it RCM. Now this triangle, we can do cosine of theta is equal to adjacent over hypotenuse, which is R over L, meaning R is equal to L cosine of theta. This is what we want to plug into our acceleration. So our acceleration in the radial direction is omega squared L cosine of theta. This was our acceleration value. So not everything was wrong. All of this was wrong. This was correct.
It's not everything was wrong.
No, yeah, but this is correct. So let's just redo the problem. The free body diagram is indeed correct, and so we want to do F net in the R direction. There's only tension in the R direction, which we said was T cosine of theta. But Newton's second law tells us that this is mass times the acceleration in the radial direction, which we just discussed is not just omega squared L, but it has that theta component because the R was actually supposed to be the circular motion trajectory. So it's m omega squared L cosine of theta. Meaning when we plug both of these in together, T cosine of theta is m omega squared L cosine of theta. Now the cosines cancel. T is equal to m omega squared L. And this looks much simpler. But this is where, I'm trying to emphasize, you guys have to be precise about what the variables mean. In the v squared over r, or the acceleration, it is of the radius of the circular motion, not the radius of, whatever information you're given, or not the length scale of whatever you're given. It has to be specifically of the circular motion trajectory. All right. So here, I know the angle dependence did get canceled out, but you're going to see in your problem set, the angle dependence doesn't always cancel out. You're actually going to get some hefty looking expressions. But hopefully we dealt enough with it in kinematics that you guys should be adequately prepared for what is to come for the problem set next week. This is not going to be on the quiz tomorrow. All right. Well, this is all we got to, and so we will call it a day, and we'll see you guys tomorrow.
Thanks, Rob.